This is video 11.6 on recursion and special sequences. First of all, we're going to kind of talk about something that's kind of cool, known as the Fibonacci sequence. It says that the seeds in the center of a sunflower show an example of a pattern often found in nature. The number of counterclockwise spirals is 8, and the number of clockwise spirals is 13. Now, these are two numbers in a famous pattern of numbers called the Fibonacci sequence. It's named after its discoverer, Leonardo Fibonacci. So what they're basically, and you can kind of see these spirals in here that all of a sudden spiral off. Oftentimes these spirals, or how many numbers are in a certain, flower or plant or anything found in nature, these numbers are found in this sequence, and it's just kind of a rare, crazy thing out there. And if you have time, definitely go to this right here, and it talks more about the sunflower seed spirals and the Fibonacci sequence. Now, the sequence of numbers is as follows right here: 1, 1, 2, 3, 5, 8, 13, 21, 35, 55, 89, 144. Now, because we just got done talking about arithmetic sequences, geometric sequences, adding and or multiplying to get from one number to the next, that's kind of what you think about. Okay, but do you see anything like that in this pattern? How do we get from 1 to 1? You add 0, or you multiply by 1. Okay, well, that doesn't work for the rest of them. So today we're going to be talking about sequences that don't necessarily fit that kind of mold. Okay, so how did Fibonacci come up with this? Take a look. Take a minute to figure this out. See how did he come up? What is the pattern here? What's going on? Now, this one's pretty hard to see, but what you can see is that the first term is a 1, and then if you take a look at the first two terms and add them up together, you get the third term. Take the next two terms, add them up together, you get the next term. 2 and 3 make 5. 3 and 5 make 8. 5 and 8 make 13. That simply, right there, is known as the Fibonacci sequence. So once you see it and once you know what he did, he doesn't seem like too much of a genius. So what did he do to get to this? How did he come up with this? Well, he started with a 1. Okay, so he just started with a 1, that's simply. The next one is a 1 as well. So he just added another 1. Now the third term, it's a 2. How did he get the 2? Well, he took a1 and he added a2 to it, and he got 2. How did he get the next term, which happens to be a 3? Well, he took a2 and added a3 to it, and he got a4. So again, same thing, a3 plus a4, and he got a5, which is 5. a5, or a4 plus a5, and so on and so forth. Oop, this one we actually have to write out the formula, sorry. So, the nth term, I didn't notice this nth at first, I thought it's at the 6th term. The nth term, how do you get from one to another? What's the pattern here? Well, we're going 1, 2, 3 here, and we're going 2, 3, 4 here, just up by 1. So what we're actually doing is we're taking a, and we're taking our n, whatever we're started with. So notice here, we have 3 here, and we have 1 here. 4 here, 2 here. 5 here, 3 here. So we're going down by 2. So we're taking our n and we're subtracting 2. And then we're adding to it. Now, how do we get from 5 to 4? Or 4 to 3? Or 3 to 2? We're just subtracting 1. So we take a to the n minus 1. And that gives us our a to the nth number. So, a recursive formula. This again is an example of a recursive formula. Is a couple things. The value of the first terms, terms. Basically, it's a formula, which is what we just wrote out here. This is a recursive formula. It's a formula that shows how to find each term from the terms before it. Now, in order to find a recursive formula, you have to know what some of the numbers are before it. You have to know how your sequence starts. Otherwise, you don't know, you can't figure out how it works or what's going on. So let's take a look. Talking again about some of the sequence types that we've already discussed. Take a look at this first one, 9 to 13, 13 to 17. Now, it's going up by a constant number, which means that we are adding a certain number to get from one number to the next. So this is just known as an arithmetic sequence. Remember, you're adding a number to get from one number to the next. Now, what are we adding? Well, to get from 9 to 13, we're going to add 4. So our recursive formula would be a of n plus 1 equals a sub n plus 4 when our a sub 1 is 9. And we're also going to specify here that n has to be greater than or equal to 1, okay? Which means, and most of them are always going to start with 1. All this means that our first term is going to start with a 1. Like our first term is our first term, okay? The pattern starts right away. Right away we can see 9 to 13, we added 4. Now Fibonacci is going to change a little bit because this pattern doesn't start right away. He starts with a couple ones first, and then we start seeing the pattern, okay? So all this is telling us is how to get from the one number to the next. Well, we're taking our first number, and we're adding 4. Then we're taking that number, and we're adding 4. And we're taking that number, and we're adding 4. And we're continuing to do this and do this. How about a geometric series, or sequence? Like this next one, which means that we're multiplying by a certain number to get from one number to the next. Well, the 7 to 21, we're going to multiply by 3. So, in this case, our recursive formula would be a of n plus 1. So how do we get from the next? We're always going to start with a of n, and then we're going to multiply by 3. And of course, we do have to tell our reader, or whoever's looking at this, what our first term is. They need to know where to start. And then this sequence does start right away, so we're going to put n is greater than or equal to 1. Now Fibonacci is the last sequence type on this little chart here, and Fibonacci is his own kind of formula, or his own kind of pattern. How do we get from one to the next? Now we did already do this. We're going to write a sub n equals, we already wrote it up here, a sub n minus 2 plus a sub n minus 1, and that gives you your formula. Now, our person needs to know, our reader needs to know what our first term is, and they actually need to know what our second term is. But after that, they can figure out what the next terms are. So n is greater than or equal to 3. So they know where to start. They're going to start at the third term on this one, because we have given them the first two terms. Because the first two terms don't have really anything to do with the pattern. Now, examples of these types of things that you're going to do for this section. Number 1 says, find the first 5 terms of the sequence in which a sub 1 is 5 and a sub n plus 1 equals 2 times a sub n plus 3 when n is greater than or equal to 1. Basically, they're giving you this and you are finding this. Okay? Pretty easy. It's tough to go the other way around, but it's pretty easy once you know the formula in order to find this. So, find the first 5 terms. One of them's already done for you. A sub 1 is 5. Right? Got it. Where should we write that? Let's write that right here. A sub 1 is 5. Okay? Now, we need to find a sub 2. Well, in order to do that, we're going to use this formula here that they've given us. So basically saying, when n equals 1, a sub 2 is going to equal 2 times my a sub 1, my last term, plus 3. That's what this is telling me. Take your last term, multiply it by 2, and then add 3 to it. So I'm going to take my last term, which is 5, multiply it by 2, and then add 3, and that's going to give me 13. Okay, how about if n is 2? So let's plug that into this formula. So if n is 2, 2 plus 1 is going to give me my a sub 3. And if I plug a 2 in here, 2 times my a sub 2, so 2 times my last term, which is 13, plus 3, Let's simplify that. And that's going to give me 29. So all I'm doing is multiplying my last number by 2 and adding 3 to it. Okay? Once you kind of get the hang of these, you don't even have to almost show any work. A sub 4. Well, that's when n is equal to 3. So take my last term, multiply it by 2, add 3 to it. 2 times 29 plus 3 is going to give me 61. When n is 4, which is my a sub 5, take my last term, multiply it by 2, add 3, and that's going to give me 125. And then basically I'm just going to summarize that out. So my first 5 terms were 5, 13, 29, 61, and 125. I feel like your book directions make this sound a lot more difficult than it is. So remember, you're just going from one number to the next, and you're using the number before it. That's all that series are about. Okay, let's take a look at another example. Number 2, find the first 3 iterates, okay, new word here, of the function for the initial value of x0 equals 1. Now, iterates are kind of still the same, like, you're still looking for, they just kind of use a different word, basically, is what it is, and they call it x of 1 instead of a of 1, okay? They give you a starting point as x of 0 is 1. This is like your a sub 1 is 1. This is like your sequence starts at 1. Why do they call them different numbers or different names? I'm not quite sure. They also tell you your formula. How do we get from 1 to the next? Well, we multiply the last one by 3 and then add 1 to it. That's all we are doing. So we're going to start off with what they told us. I'm just going to rewrite this formula. F of x equals 3x plus 1. And I'm going to start with what I know. I know x of 0 is 1. So that would mean that f of 0, whoops, equals 3 times 1, I'm getting that from right here, plus 1. 3 times 1 is 3, plus 1 is 4, so my x of 1 is 4. Do it all over again. F of 1, I'm sorry, F of 4 I meant, I'm putting that number in. You know what? I feel like we could write this a very much easier way. We can. I'm sorry, so x of 0 is 1. To get to x of 1, and x of 2, and x of 3, which is what we want to do, we're going to start by using this. So I'm going to take my 3 times my last number plus 1, so I'm just taking this formula here, just plugging in my last number into that spot, and I'm going to get 4. Do it all over again. 3 times 4 plus 1, that's 3 times 4 is 12, 12 plus 1 is 13. Do it all over again. 3 times 13 plus 1. It's going to give me 39. 39 plus 1 is 40. Now, we only wanted correct the first 3. Yep, and we got them. 4, 13, and 40. And there's our answer. So we could write it out a little bit nicer, otherwise you can keep it like that. So, again, same thing, just different vocabulary, basically. Now, an iteration sequence, this is kind of what we just did up here. It's used more often in real-world situations. And I'm going to show you an example of the next one. For example, like compound interest. So if you buy something and it causes interest on it, house, car, anything like that, and we do need an initial value in order to do this. And oftentimes they're going to say that that's x of 0. Okay, so we do need that initial value, that x of 0, or whatever it may be. Okay, so let's look at a real-world example now. It says Henrietta's parents started a savings account for her when she was born. They invested $500 in an account that pays 6% interest compounded annually. Find the balance of the account after each of the first 3 years. So now our initial balance, our x of 0 in this case, was $500. That's kind of our initial value, just like they were talking about up here that we need to have in order to do this problem. So let's label this as our initial balance. Now, that's when she was born. They put that money in. She's not quite 1 yet, right? She was just born. So, first year. So when the baby turns 1. 1 year old. 1 years. Not 1 years, 1 year. Okay, 1 year old. Let's do that. So when the baby's 1 year old, that $500 has increased. So 500 plus. But plus what? Okay? What we need to do is it says because the account pays 6% compounded annually, meaning that once a year, annually is what that means, that interest is going to be put onto the account. So let's just say when she turns 1, it's put onto the account. 6%. So it increases by 6%. So this $500 is going to increase by 6%. Now in order to find that, we're going to change the 6% to a decimal, which would be 0.06. So 0.06, let's write down. And we're going to multiply that by $500 because that's how much was in her bank. So, solving for that, $500 plus 0.06 times 500 is going to give you 30 is $530. So when she's 1 year old, her balance is now $530. How about when she turns 2? So we're finding the balance of the account after each of the first 3 years. Now, do you think it's just going to go up by $30 again? Is it going to be $560? Let's check it out. So the balance now is $530, and we're going to add to it again a 6% raise. So 0.06 times the balance of 530. So now notice, we're not multiplying by 500 anymore. These two numbers have changed. Okay, it goes off of the last number we had in the sequence, just like all the ones we had just done. So we have $530, and it's actually going to increase by $31.80 because that's what 0.6 times 530 is. So if we add that together, our new balance now is $561.80. There it is. That's how much she has at 2 years old. How about 3 years old? Last one, right? We could keep doing this and keep doing this, but they just want the first 3 years. So $561.80, and we're going to add again a 6% increase, so $561.80, changing those two numbers, multiplying together, 0.06 times 561.80. Actually, I don't have a number on that one. I just have a total. Is going to give us $595.508. So let's just go ahead and round that to the nearest penny. So $595.51. Let's round that too. So her first 3 years, first year she got $530. Keeps it in the bank for the second year, you get $561.80. Keep it in the bank for a third year, you get $595.51. Just on interest. Isn't that sweet? So when she was a baby, she only had, or when she was born, she only had $500, but by her parents keeping that money in a bank for 3 years, it has increased almost $100. Very cool. So that's again kind of something how you can use sequences in an everyday pattern.